Hi guys, this is week 6, video number 1. So Chem 4, week 6, this is the first of 3 videos this week. This video is all Lewis structures, start to finish, how to draw the Lewis structures, okay? Has nothing to do with Vesper theory yet, that's the next video. Right now we're just learning how to draw Lewis structures, which is how to connect the atoms properly when drawing a structure in 2 dimensions, like on paper. All right, so top of page 1, it says rules for drawing Lewis structures, okay? So before we list the 5 rules with examples, we'll do 6 examples all the way throughout. Before we list the 5 rules with examples, remember these 3 general things. Hydrogen and the halogens, I, F, Br, and Cl, they only make one bond. So you're only going to see one dashed line to them for the most part. They only make one bond. They have one dashed line coming off of them. They like to be on the end or the outside of the atom. Second thing to remember, don't put more than 5 bonds around the central atom. So 4 connections, right? 4 bonds, up, down, right, left, maximum. Don't put more than 4 bonds around the central atom unless the atom is period 3 or lower. So that unless statement we won't need to worry about too much. In general, don't put more than 4 bonds around the central atom. All right, the third bullet point to remember before we get into the rules, a bond, and I got an example bond there, X dash X. That dash, by the way, is a covalent bond. Lewis structures are drawn for covalent molecules, not ionic, and they count as 2 valence electrons shared by each atom contributing to the bond. All right, so here are the rules with examples as we go. We got 5 rules. Rule number 1, determine the total number of valence electrons in the atoms to be combined. So valence electrons, remember, you look at the group number, the vertical group number that the atom is in. If it's group 1 or 2, it's got 1 or 2 valence electrons. If it's group 13, 3 valence electrons. Group 16, 6 valence electrons. All right, so groups 13 through 18 then would have 3 through 8 valence electrons respectively. Example 1, CH3I, carbon, 4 electrons. Hydrogen total, 3 times 1 electron. Iodine, group 17, 7 electrons. Example 1, CH3I has 14 total electrons. CClH3 in the same way also has a total number of valence electrons, okay? So this is rule number 1. You notice I'm not going straight into the structure. I'm just counting up the total number of valence electrons. I and Br are both group 17, so 7 valence electrons each, total of 14. NH3, nitrogen 5, hydrogen 1, 3 times is 8. All of these circled electron counts are the total number of valence electrons. It should always be an even number, okay? All right, so those 6 examples, I've just looked at their group numbers and I've added up the total valence electrons. Rule number 2, arrange the atoms to form a skeleton structure. This is like an outline of the way we think it's going to look. Arrange the atoms to form a skeleton structure for the molecule. If carbon is present, it's the central atom, all right? So if carbon is in our molecule, we make it the central atom. Otherwise, the least electronegative atom is our central atom. Don't worry too much about that last sentence. By and large, we will kind of, just through symmetry, know who the central atom is going to be. All right, so arrange the atoms to form a skeleton structure for the molecule. If carbon is present, it's the central atom. You never want hydrogen or the halogens to be a central atom. And then the last statement there, then connect the atoms with electron pair bonds. So CH3I, make my connections. For example 2, this is CClH3, make my connections. Just making connections, right, with bonds. Each bond is 2 electrons. IBr, Well, IBR, there's no other way to connect it. There's no true central atom with IBR. You need 3 atoms to have a central atom. In example 4, I put my N in the middle and I put my H's. I spoke my H's out, up, down, right, left, either way I want. All right, so for example 5, how am I going to make the connections? Well, I put boron in the middle, and then if I think symmetry, I just put my H's on one. I put one up, right, left. You could have put one down, it doesn't matter. Example 6, sulfur with hydrogen on the outsides. Now, why did I put them on the outsides? Well, you want to get in the habit of putting atoms as far away from each other as possible, because those 2 dashes are an electron pair, and electrons repel each other. So I put my dashes away from each other with the HSH. Rule number 3, freely add lone pairs of electrons. Always add them in groups of 2. Whenever you add lone pairs to a molecule, you add them in little sets of 2, little double dots. Always. Never add single electrons. Freely add lone pairs of electrons, which is 2 electrons, so that all atoms are happy with 8 electrons around them. Okay, now remember some exceptions. Hydrogen only likes to have 2 electrons around it. Boron only likes to have 6 electrons around it. All right, so I'm going to write that down now. This is called the octet rule. Everyone likes to have 8 electrons around them total. But don't forget that hydrogen only wants 2 electrons. Boron only wants 6 electrons in order to quote unquote be happy with 8. Now at this point in time, we are ignoring rule number 1 and the number of valence electrons. We're just trying to make everyone happy. Then we're going to check the electron count to see if it matches rule number 1. So in rule number 3, we ignore total electrons. We just make everyone happy with 8. So the H's are okay in examples 1 and 2. We have to make the iodine in example 1 and the chlorine in example 2 happy. We give them each 3 lone pairs. Example 3, IBR, we need to add lots of lone pairs to give everybody 8 total around them. Example 4, just the nitrogen needs a lone pair. Example 5, boron. Looks very similar to example 4, but in example 5, boron is good as he is. All right, and then H2S, the very last example 6 on the last page, we had to give sulfur 2 lone pairs. Now we're going to look at what we've done in rule number 3 and see if the electron count matches to rule number 1. So this is rule number 4. Count the total number of electrons in the skeletal structure, right? Because in rule number 3, we just added lone pairs everywhere to make everyone happy with 8. Rule number 4, count the total number of electrons in the skeletal structure to see if the amount of valence electrons used equals or matches the number of electrons that we agreed it had to have in rule number 1. Okay? So rule number 1 wasn't just bookkeeping. We had to do that rule number 1. Before you draw structures, you're actually not drawing structures. You're counting valence electrons in that rule number 1. Anyway, a note here on number 4. We're going to rewrite our results to rule number 3 so we can see them on this page of paper, just to see if we have to do anything for rule number 4. So it says, note, we're going to rewrite our result of rule number 3 below to make this rule number 4 easier to understand. So in example 1, 14 electrons available. We had that from the very beginning, rule number 1. And rule number 3, our result looks like this. We have iodine. So if we count up all the electrons, 2, 4, 6, 8. Those are for the dashes. 2, 4, 6, 8. And then 10, 12, 14 for the lone pairs. This thing is all checked out. This is actually finished. Okay, but we'll carry it through to rule 5. Example 2, 2, 4, 6, 8, 10, 12, 14 electrons is what we have. 14 electrons is what we were supposed to have at the end from rule number 1. Example 1 and 2 are actually done already. Finished. Those are the Lewis structures. Example 3, BH3, we remembered that boron was an exception. He likes to have only 6 electrons around it. 2, 4, 6, this one checks out. Example, it should say example 4. Example 6, it says. Example 4, H2S, so the 8 electrons available. Sulfur has 2, 4, 6, and 8, checks out. All right, so rule number 5 is the following. It says, if and only if too many electrons were used, which was never the case just now in Rule 4, okay? We're going to do this again where Rule number 5 comes into play. Rule number 5 is not really going to come into play here for this first round. If and only if too many electrons were used in Rule number 3, we have to remove one or more lone pairs and throw them in the trash. Throw them away. We'll never use them again. We're not going to bring them in and make double bonds or anything. They are gone in the garbage. Erased. So if and only if too many electrons were used in rule number 3, remove or erase one or more lone pairs, and the lone pair is 2 electrons, from the central atom. Central atom is the boss. He's the head honcho. He's the one who sacrifices the 2 electrons if we have 2 electrons too many. All right? So the lone pairs that you just erased are gone forever. And then it says there in the little bullet point, it says now, move one or more lone pairs to existing single bonds to make double or triple bonds. And the reason why we would do rule number 5 is so that we can get everyone with a complete octet. Everyone likes to have 8 electrons around it. But sometimes when I apply rule number 5 and erase some electrons, some of the other atoms get screwed and they don't have 8 electrons around them. All right, so for most of this first round, these 6 examples, rule number 5 is not necessary. But later in this exact video, I'm going to do some where rule 5 is needed. That's when we have double bonds and triple bonds. So you can see as I'm going through these examples down below right here, rule number 5 not necessary for example 1. Rule number 5 is not necessary for example 2. Why is it not necessary? Well, because my electron count from the end of rule number 4 matches rule number 1 electrons available. CH3I, 2, 4, 6, 8, 10, 12, it's got 14. Done. Example 2, CClH3, 2, 4, 6, 8, 10, 12, 14. So in example 2, I've got the proper number of electrons already that I need for rule number 1. Rule number 5 is not necessary for example 3. IBR is finished. I put a box around the finished Lewis structures here for examples 1, 2, 3, and 4. The NH3, 2, 4, 6, 8, and that matches rule number 1. So these are finished. I have not had to apply rule number 5 there. I just basically rewrote my results from rules 3 and 4. You're going to find out in example 5 and example 6 that we don't have to apply rule number 5. So the Lewis structure is just as is. BH3, 2, 4, 6 electrons. Everyone's happy. The hydrogens only have 2 electrons. That makes them happy. And rule number 5 is not necessary for example 6. So my final Lewis structure is H-S-H with 2 electrons, 4 electrons around sulfur. Those are 2 lone pairs. Now, why did I just do rule number 5 and then not apply it? Now I'm going to do a second round where the molecules are a little more difficult, and now we're going to apply the rules. Okay, so this says right here, repeat. Rules for drawing Lewis structures. Different examples. I got 6 new examples now. Okay? So I'm going to rewrite the rules. I'm going to be very exhaustive with this. You definitely want to know how to do Lewis structures. So I'm literally rewriting the rules all over again and going through a second round of 6 examples for you. Okay? So I'm not doing this for my health. I'm doing this so you guys can learn this stuff. All right? Number 1, we determine the total number of valence electrons in the atoms to be combined. We use the periodic table. We find out what group the atom is in. If it's group 1 or 2, fine, it's going to have 1 or 2 valence electrons. All of the atoms we see will be on the right-hand side of the periodic table. So carbon, group 14, 4 electrons as an example. You count up the electrons, and you see I've done it in example 1 and example 2. It's always an even number. So where are we? Example 4, CO, carbon, group 14, 4 electrons. Oxygen, group 16, 6 electrons. So example 4 has 10 valence electrons. Those aren't the total electrons. Those are the valence electrons, the outermost electrons involved in bonding. Example 5, carbon group 14, oxygen group 16. We end up with 16 electrons, 16 valence electrons. Example 6, HCN, hydrogen 1 electron, carbon 4 electrons, nitrogen 5 electrons, for a total of 10 valence electrons. Rule number 2. Arrange the atoms to form a skeleton structure for the molecule. Remember, if carbon is present, it's the central atom. Otherwise, it's the least electronegative element. But if you think symmetry, and if you think if you look at the way the molecule is written, you can kind of, I don't want to say sound out, feel out, but if you just think symmetry, symmetry will help you rather than use this least electronegative term. Okay? But I do have to put that in because that is the rule. So rule 2, arrange the atoms to form a skeleton structure. You're thinking symmetry, all right? If carbon is present, make him the central atom. And we're just doing connections right now. Rule number 2, there's no lone pairs involved. Skeleton structure is just making bonds, those little dashed lines that represent 2 shared electrons. All right, so for example 1, I just put my carbon in the middle. I put 3 H's around the carbon. I attach an N and 2 H's around the N. I could feel that's kind of how it was going to look just based on the way the molecular formula was written for me. Example 2, carbon in the middle, attach an O and H, thinking symmetry. Example 3, 2 carbon center here, right? There's no real center in example 3. I have a 2 carbon center, but I'm thinking symmetry, so I put an H off of each carbon, all right? So there's no true center in example 3, and I'm thinking symmetry. Example 4, all you got to do is just do a C-O. There's no other way to do example 4. Didn't put any electrons in, did I, for rule number 2? Nothing. Not doing that yet. That's rule number 3. Rule number 3, we make everyone happy. Not yet. CO2, carbon in the middle, oxygen's on the outside. For example 6, carbon in the middle, put nitrogen on the right, hydrogen on the left. If you wanted to put nitrogen somewhere else, you can. I'm just making connections. It's just a skeleton structure. Now we get to add lone pairs in rule number 3. Rule number 3, freely add lone pairs of electrons so that all atoms are quote-unquote happy with 8 electrons around them. Now, on a quiz, on a test, and in the homework, you basically do the rule right on top of each other. So if you're using a pencil, right, you just do this as you go in one space. I'm going through them all so you can see the rules. So example 1, what we had so far was the following. CH3 up there with an NH2. Only nitrogen needed the lone pair and to have a total of 8. Everyone else was fine. Example 2, carbon needs 1 lone pair. Oxygen needs 3 lone pairs so that everyone's happy with 8 electrons. In example 3, each carbon needs 2 lone pairs. In example 4, carbon needed 3 lone pairs and oxygen needs 3 lone pairs. In example 5, to make everyone happy with 8 electrons, carbon needs 2 lone pairs and each of the oxygens on the outside needs 3 lone pairs. In example 6, carbon needs 2 lone pairs, nitrogen needs 3 lone pairs. I never counted the electrons. All I'm doing was making everyone happy with 8 electrons around them. Okay? Rule number 4 is when I count to see, geez, how many electrons did I just throw in there total now? And I checked out with rule number 1. Okay, so then rule number 4 says count the total number of electrons, and then we're going to compare it to the number of electrons that we're supposed to have in the end from rule number 1. So it says if the amount of valence electrons used equals the number of electrons available from rule number 1, then you're done. You can put a box around what you have and call it the Lewis structure. All right, so we got to do plenty of that in the first round of examples. Not so with these more advanced 6 examples. So example 1, 14 electrons were available from rule number 1. This one actually checks out. 2, 4, 6, 8, 10, 12, 14. Boom. Done from rule number 3. I'll carry that through, but that's actually finished. Example 2, 12 electrons were available, and at the end of rule number 3, what did I have? I had how many electrons? 2, 4, 6, 8, 10, I had 14 electrons. Uh-oh. That's 2 electrons too many. How many electrons too many? 2. How many lone pairs is that? 1. Who am I going to erase that 1 lone pair from? Eventually, in rule number 4. Or maybe it's rule number 5. I'm going to erase that from carbon, but not right now because I'm doing a bunch of examples together. Example 3, 10 electrons available from rule number 1. So I have 2, 4, 6, 8, 10, 12. I have 14. That is 4 electrons too many. How many lone pairs is that? That's 2 lone pairs. 2 lone pairs too many. Eventually I'm going to have to erase that when I address it. Example 4, from rule number 1, I have 10 electrons that I'm allowed to have at the end of all of this. What I have so far is 2, 4, 6, 8, 10, 12, 14. That is 4 electrons too many, which is 2 lone pairs too many. All right? So who do we erase electrons from when we get to it? The boss, the central atom, carbon. Right? We'll get to that when we get to the right rule. We still have 2 more examples. Example 5. Well, from rule number 1, for example 5, we know that we are allowed to have 16 electrons at the end of all of this. Okay, so far, what do I have? Well, I have 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 20 electrons. 4 electrons too many. I'm going to have to get rid of 2 lone pairs. You can see the 2 lone pairs sitting on the carbon. I'm going to have to erase those and throw those in the trash. All right, example 6, from rule number 1, I have 10 electrons available. All right, so what I have right now is I have the following structure that has 2, 4, 6, 8, 10, 12, 14 electrons. Yet again, 4 electrons too many. So I'm going to be very busy in the next rule here, erasing electrons. All right, so let's rewrite the rule, and then we'll bring those 6 examples in and take care of them. Number 5, rule number 5 says if and only if. We didn't have to use rule 5 at all in the first 6 examples. We have to use it on 5 of these 6 examples. It says if too many electrons were used in rule number 3, erase, in other words, remove 1 or more lone pairs from the central atom and throw them in the garbage. They're gone. They're not going to be used later to make a double bond or a triple bond. They're trash. You'll never see them again. Okay? So, 5. If too many electrons were used, in rules number 3 and 4, erase or remove 1 or more lone pairs from the central atom until you get your total number of valence electrons remaining down to what you need for rule number 1. The lone pairs you just erased are gone forever. Ignore them. We will use other electrons to make double bonds, not the ones we just erased. So it says now move 1 or more lone pairs to existing single bonds to make double bonds or triple bonds. Now, why do you do this? Well, rule number 5 makes me erase the electrons from the central atom. And when I erase electrons from the central atom, that's not going to make the central atom, quote, happy with 8 electrons anymore. So I need to donate in from outside atoms to make double bonds or even a triple bond, because you have to have 2 things at the end. The right number of electrons, and everyone has to have an octet, except for boron and hydrogen. So example 1, rule number 5 is actually not needed. Everyone's happy with 8 electrons, and electron count is in check. Now in example 2, 2 electrons too many. So I'm going to have to remove 2 electrons. In other words, I'm going to have to remove a lone pair from the central atom. All right. So I'm going to squeeze this in down here, and you see that I'm going to rewrite it. So I have going to remove 2 electrons from carbon. They're gone. If I draw the second structure, you see they're no longer there. That gives carbon only a total of 6. Not good. So we move that lone pair in from oxygen, right? You notice how we moved the lone pair that was still on the molecule, not the lone pair that we threw in the trash. All right. So example 3, 4 electrons too many. All right. So I am going to have to remove 2 lone pairs. Thinking symmetry now, I'm going to remove my 2 lone pairs. If I rewrite my example 3, what I have so far, it was a 2 carbon center. So I'm going to go like this, remove 2 lone pairs. I'm going to do this all stepwise so you can see. So if I remove the 2 lone pairs, one from each carbon, they're gone. And then what lone pair am I moving in to make a double bond and then eventually a triple bond? I'm moving the lone pairs that are still on the molecule, not the ones that I trashed. Okay? So watch the stepwise movement of the electrons here. Moving the electrons in to make a double bond. Why did I do it again to make a triple bond? Well, I did it again because the carbon on the left still only had 6 electrons total around it. All right? For example number 4 now. We've got 3 more examples to get through on this. For example 4, if you remember, I had 4 electrons too many. 4 electrons too many means I have to remove 2 lone pairs. So here's what I had. I had CO single bonded with a bunch of electrons around it. I have to remove 4 electrons. Well, I chose to remove them from, I should have removed them probably both from carbon, but it doesn't really make a difference here. I removed my 4 electrons and they're in the garbage. Now in step 2, you see I donate in from carbon to make a double bond. Count up everything at the double bond. You got the right number of electrons, of course, but the carbon only has 6. Do it one more time, make a triple bond for CO. The example 4 result, you've got your 2, 4, 6, you got 10 electrons in octets. Example 5, okay, 4 electrons too many. We remove both of them from carbon, and then we're going to think symmetry. We're not going to keep a single bond, triple bond. We're going to donate in each time to make a double bond. Why do I have to make 2 multiple bonds? I got to get carbon a total of 8 electrons around it. At the end of a Lewis structure, you have to have the right number of electrons from rule 1, and everyone has to have their octet satisfied. Okay? All right. Example number 6. We're almost home. Long video. So 4 electrons too many in example 6. So we're going to remove 2 lone pairs. Okay? Starting to sound like a broken record here. We remove the 2 lone pairs from central atom carbon. You'll notice I've done that in the very first step. In the second step, I donate in from a nitrogen. I could have donated in from any of the 3 electron pairs. And I have a double bond. The double bond isn't enough because carbon only has 6 electrons. Try it one more time. There you have H single bonded to carbon with a triple bond N. 2, 4, 6, 8, 10 electrons from rule number 1. Everyone's got an octet satisfied, which is 8 electrons around it, except for hydrogen, who likes 2. So this is how you do Lewis structures. Okay? Lots of homework problems on this. You need to know how to do this. All right? So I'll see you in the next video. We'll talk about VSEPR theory.